Well, here we discuss this very almost trivial. I remember when I first introduced this, I called it embarrassingly parallel. This was a talk I gave in 1988, and I was analyzing parallel computing. And at that time, I said 20% of the applications were embarrassingly parallel. And people found these applications were so important that somehow to give them a slightly negative context of embarrassing was not good, so they were renamed pleasingly parallel, which is the term I now use. It is, these are the simplest form of parallel computing, but they're an incredibly important class of parallel computing problem. And here we have a few remarks on which we'll go into a little more detail. We'll give more examples later on in this course. Parallel computing involves organizing a set of computers to solve a problem. And when you organize them, you better make certain they're working on the same problem. You have to coordinate with them. And whenever you coordinate, you have to communicate. Remember how you get told in life, improve your communications, Jeffrey. You're not communicating well. You're making ad hoc decisions and not telling anybody. So computers aren't allowed to do that. Computers have to communicate, because if we don't tell them what to do, they won't do the right thing. So organizing our computers is very important. And in the case of the simplest organization is pleasingly parallel. Each job in this sort of simplest version of this, each job starts, reads some of its own data, and then it writes it out. We're still using the single program multiple data. Each computer or process or thread is typically running the same code. It can be at different parts of the code at a given time, but they typically are doing the same thing. And but the nature of the problem is they can do that thing independently. Here's what I call local machine learning. And if I looked at, like, say, a Croesus application, there's incredibly sophisticated, it's not really usually called machine learning, it's called signal processing, takes the raw data from the radar and converts it into images which have the reflections and isolate the reflections, which enable us to determine the snow layers and the glacier beds. And so if you take, this is typical of many experimental sciences, where you take so-called, and these actually, unfortunately, using the word event again, these are experimental observations, and those observations you just take lots and lots and lots of them to cover everything. The case of Croesus is because we want to cover the entire area of Greenland or the Antarctica and the Arctic. And to do that, we do that with lots and lots of separate images, each covering a small region. In the case of particle physics, we take several billion collisions each year, and each of those collisions is independent, and you need that number of collisions to be able to cover the full range of possibilities and find the rich set of things you're trying to find. It's worth noting for this LHC case that each of those events is about 1.5 megabytes. That's for the so-called CMS and ATLAS experiments. And then you have to take the raw data, which is very messy. I used to work in that field. Those are messy experiments, because you're recording the particles produced in a high-energy collision, and you do that by tracking these particles through various chambers, which the particles interact and record their presence, and you have to convert that recording of their presence into a measurement of the nature of the particle, and at least know its charge, and also whether it's a pi meson or a k meson or a photon or an electron or what have you, or a proton. And that conversion of the raw data into a list of particles for, say, the ATLAS and CMS experiments is about 10 to 20 seconds running on a core. So you have several billion independent 10 to 20-second computations. And they're all independent, so this is a pleasingly parallel problem. Note, when you run a job for the LHC, you don't run a 10-second job. You process a file which has enough events so that the job lasts maybe an hour or so. Because setting up a job and getting it started takes time, so you have enough events there so that the startup time is small. Plus, you don't really want to write typically this field uses files. It doesn't use HBase or anything like that. It doesn't have a data management thing underneath it. And you wouldn't want one file for every event. You do not need several billion files. Actually, this problem is, of course, not really totally and pleasingly parallel, because there was one answer. There is a Higgs boson. So there are some correlated activities, and these are in the make it really of the MapReduce stack category, because it has global reductions to do histograms, to find averages for calibrations, but it's a very minor part of the computation compared to these pleasingly parallel parts. So it effectively is pleasingly parallel. Another good example of pleasing parallel, which you'll see in the classification of the use cases, is the Internet of Things, because each sensor is typically processed independently. Another class we discussed was data assimilation. So we need to bring everything to bear to solve problems, and so we need to do observational science and simulation science, or high performance computing, computational science. And typically, you're taught to do that by solving differential equations. Differential equations have boundary conditions and initial conditions, and then you solve them. But that's not really quite correct, because that assumes you know everything. And say, even when you do something very well studied like the weather, you don't know everything. You don't really know the composition of the atmosphere perfectly. You don't know the wind velocity perfectly. So there are many uncertainties. And so, although you basically set it up as a traditional partial differential equation solver with initial and boundary conditions, you can do what's called data assimilation. You can you can take effectively redundant information, because you have a simulation, it gives you an answer, and then you compare it with the observations. But actually, you're not really trying necessarily to compare the calculation with the observation. You actually want to tell somebody what the weather is. And so the best way to tell them what the weather is to combine the data and the observation. Sorry, combine the simulation and the observation. That's called data assimilation. The goal is to produce the best possible forecast of what's going on. And so you use everything. That's the basic idea of fusion. And it's a well-known principle of big data. The way to get more understanding is to combine multiple sources of data. You look at users and products on Amazon. You don't look at just users or just products. So data assimilation is a very old technology. It's been used for a long time. I used to work on that about 20 years ago with NASA Goddard, and it's still very important. Another category, which is actually a little more recent in terms of at least its popularity, which is so-called crowdsourcing. Here, we don't actually use the computer. We may use the computer to organize things, but we use people to solve problems. A good example of where they might be useful is you have a whole bunch of images, you're searching for some hidden thing in those images. Probably people, at least historically, people are probably better than humans. People are better than computers at doing image processing. The problem is computers are faster than people. And however, so how do you solve that? You solve that by using a lot of people, the big people approach, which goes hand in hand with big data. So that's crowdsourcing. Use lots of people to correct either things that are unknown or wrong in data. So, good example is the wonderful thing called Wikipedia, where people edit other people's work and correct it, and we eventually end up with a much better description of many things using this crowdsourcing strategy. There was a use case 29, which studies people for which crowdsourcing was highlighted and is very natural. Well, we already discussed high performance computing and its importance. There is a class of computing which is typically a little on the edge of high performance computing, namely agent based modeling. And so, when we were doing our material science, we had a nice, pretty picture of a new nanomaterial. That uses fundamental Newton's laws or Schrodinger's equation or Dirac's equation, the fundamental equations of matter to describe atoms, electrons, and molecules. You want to not just simulate materials, you want to simulate the stock market, the transportation system, or the reaction of population to disease or some unexpected shock like a 9/11 event. Then the basic entities are not subject to Newton's laws. People do not obey Newton's laws. Their behavior follows eventually from Newton's laws, but you can't make a model of people as bunches of atoms and electrons and molecules and realistically solve that to decide what they're going to do when you have a 9/11 event. Rather, you introduce a new type of science where you set up a person as the so-called agent. An agent is a computer entity which receives has a set of rules in it which tell you what it does when certain things happen. And so agent-based modeling is very important. It's been used for many years by the Department of Defense with a technology called HLA or DIS, which is used to do their simulations. And use cases 23 and 24 on spreading a disease and reaction of people to scenarios. Those use agent-based modeling, which is a very important technology for the subset of cases where it's relevant. And typically, if you read the simplest books, it will tell you to use a so-called event-driven simulation to evolve agents, but that's the world's most inefficient, slowest thing. It's the most precise and best if that's all you can do, but typically use some heuristic to make it run faster. Okay. Well, we already mentioned fusion, and we actually showed you the example of my picture ending up with a fused bottle at the top right. And there's another magic term here, knowledge management. Data fusion and knowledge management are not very well defined, except it's obvious what the intuitive meaning is clear. We have a huge amount of data, which remember is turned into information and knowledge, and we have that from many different sources, and we need to combine it to get the answer we want. And that's what data fusion and knowledge management are doing. There are many people who work in this field, and it's often rather hard to find out exactly what they do. But I believe that slide, which is mentioned here, the raw data, the decision slide, shows the essential idea. You have a workflow. Workflow is very important, and it's present in nearly a lot of these different use cases we have, where you have multiple services and clouds linked together, typically with data. Where here we're using data in this generic fashion to mean data or information or knowledge, flowing from one service to another, getting refined or transformed and filtered as it goes from one to the other, and ending up with a better understanding by, or hopefully alternative understandings. The simplest type of fusion actually is to just take a portal, take 6 sources of information about a subject and place them one in each of 6 gadgets, and that's the one form of fusion, but most fusion would be a little more sophisticated than that. When we come to global optimization, where we're summing over giant, we're parameterizing the world, summing over all the information we have, that's effectively a fusion algorithm because it's taking disparate things and adding them together to reach some sort of conclusion. So that's this exascale global optimization ego classification. So then we now come to that. So it's a rather flamboyant title, which was invented in some meeting I was at a few years ago, and it basically points out that there are a class of artificial intelligence problems phrased as giant optimization over many variables. This is what I call global machine learning. And the case that's most familiar is called chi-squared or maximum likelihood formulations, which after you take the log of the maximum likelihood, you always get, and you take the right sign, you always end up minimizing a sum of terms. And those terms are a mix of observational data or derived data and parameters which you wish to determine. And this type of artificial intelligence formulation is pretty different from the rule-based or expert system AI. And it's probably the most appropriate when you really have a lot of information, because you can try to minimize the sum of a billion terms, but you can't really reliably apply a billion rules. They will interfere with each other. Whereas if you sum them up and try to minimize them in the least squares fashion, you can get them to trade off against each other in the most satisfactory fashion. One example we have, a very simple example, is called multidimensional scaling, where if you want to solve the AI problem of mapping entities either in the non-vector space or an arbitrary vector space to 3 dimensions, then you have a global sum over n of them, essentially n squared measures of similarity, and you minimize the weighted sum of the squares of the similarities minus the predicted similarities when you assign them to a vector space. Another good example of ego, in fact, probably the most important, come from information retrieval, where you take the world's documents and try to summarize them or find topics implied by them and so on. I expect ego to grow in importance, and you could say learning networks are also in this area. I didn't really classify anything as security. When we discussed the NIST activity, we noted there was a security and privacy working group. Security is essentially present in all use cases. And the word security covers many, many areas. Authentication, authorization, how you log in and you decide that you use a computer or you access a piece of data. There are lots of privacy issues, either especially in the healthcare area, say because of personal data, or in commercial areas because due to proprietary data. We also have to worry about tampering when you have these pictures of man in the loop or whatever, attacker in the loop, where you have a nice workflow, and unfortunately one of the services has got corrupted and is stealing what the data is coming in and spitting out garbage, which confuses the world. So there are important issues in security with you do cloud computing, because cloud computing is shared computing. And so you can have, so you worry that if you have a proprietary application running, it's telling you which the company will tell you what types of calculations the company is doing, even though there is no trivial way of finding out. Maybe another program running next to that program can see what data sets are being accessed and effectively look at the execution model of that program and extract and effectively compromise the proprietary nature of the computation. So in the end, it points out that the three broad areas: commercial applications, proprietary defense as incredible national security issues, and health and social studies, and some of those in the network science area have privacy issues from the use of personal information.